please welcome Arnaud.
Thank you. Can you all hear me? Excellent. So thank you, Andres. Thank you, everybody, for being here. Before I start, I want just a bit of a disclaimer. This is absolutely unrelated to my actual day job at Twig.io. So this doesn't engage my employer in any way. So with the usual formalities done, let's move and have fun. I mean, it's going to be fun, at least if your idea of fun is writing programming languages and category theory, which I admit is a bit of a niche hobby. But since you're all here, I hope you're here to have fun with me. So let's go on. Suppose you're writing a programming language, which is the entire point. You're writing your compiler. You will have at some point to handle this thing called binders. A binder is when you introduce a name and you will use it locally to something. So here, the smallest example of a language with binder is the lambda calculus, which has basically functions as application. The function, the lambda thingy there, which is like Haskell's backslash, introduces a name x that is allowed to be used in U. So I don't know, you take a textbook, it talks about lambda calculus, and we're writing a lambda calculus interpreter this time, or something like this. Okay, so you open the textbook, you see there's variables, so let's represent variables by some kind of identifier. I don't know what it is, probably a string or a number, something that is recognizably a name. And then we can continue translating it, so a lambda term is a pair of a name and a term, etc., etc. You'll start writing your interpreter. You interpret application by doing a substitution of the V into the U. So everything seems to be working, but then you have sort of something nagging about in your mind. You say, okay, I'm going to write some quick check tests, and then things go slightly awry. For instance, you have this lambda x terms. You never really thought about writing that, but QuickCheck does that for you. You apply U, and suddenly it becomes something really, really weird. It really shouldn't have been that. This problem is the problem of shadowing, of course. That hasn't been implemented right. Oh my. And maybe you've been actually quite careful to write an interpreter that handles open terms as well. So you apply lambda x, lambda yx to y, and then suddenly the constantly y function becomes the identity. Ooh, that is bad. And that is bad because binders are really, really hard. So these sort of problems are called variable captures, sorry. And that's the reason why sometimes when you see substitutions in books, it's heavily qualified as capture avoiding substitutions, just to make sure. It means exactly the same thing as substitution, but it's so important and so easy to get wrong, and everybody has, so don't feel bad the day it happens to you, that people start qualifying and say, oh, I'd have to remember to avoid capture. So maybe you're there and say, oh, there must be a better way. And so you open another book, and it calls about this thing called De Bruijn indices. While we're at it, the initial article introducing that from De Bruijn was called Nameless Dummies. So just the name has fallen out of fashion, but it's still quite funny. So the idea is we will remove names, and we will represent variables as pointers to their binder. So in our case, it's a lambda. And the way we do that is basically we say the variables are integers, and we count the number of lambda that you skip until you get to the actual lambda. Okay, so then you start writing your lambda term data type, which is fairly easy, and then you read on to see how to implement substitution. So you need to you shift substitution, you lift variables, and you have to remember to decrease indices, otherwise there will be some troubles. And well, anyway, it's a lot of a mess. It's a super powerful technique when it's gotten right. It does a lot for you. You don't have to reason about names anymore because you don't have names anymore. But you still can get some viable captures. The Carte programming language in which I've worked for a while uses De Bruijn indices everywhere like this. There's a lot of library that is set up. However, I got variable captures an embarrassing number of times while working on this. So it's not perfect then yet. And yeah, so this is Haskell Exchange. We're doing Haskell. Can types help us? I guess, I mean, if I am asking the question. But the point is, yeah, let's find a way to do that with types. And we're going to change our view a little. So we're going to add a parameter to the data type of terms, and that represents the variables that I'm allowed to use. I'm just assuming that it is a type because it's simpler, but then it becomes quite interesting. So you say a variable is a member of the variable of the set of variable allowed. Makes sense. Application just takes two terms, makes a term, and the binders, the lambda binder says, oh. Now I need one extra variable. How to add an element to a type? Well, maybe does that quite precisely. So then, when you want to speak about the variable that this lambda introduced, you say nothing, which it's a bit mind-bending, but I couldn't have named it otherwise. But anyway, maybe. So nothing is that variable that I just introduced, and just v is what v was before I introduced a new variable. So it just skip over the lambda, and then continue interpreting my variable. So it does exactly the same thing as the Breuil indices, just counts the lambdas. Except I lied. So there's an actually good reason to say that A is like of kind star, is because now term is a monad. And why does it matter? Well, not because we like monads, though we do, I guess. No, because the join of the monad, the bind of the monad really is exactly a substitution. Says, okay, take me an interpretation of each variable as a term, and give me a term, and in that operation I can change the free variables of my term. That's pretty cool. So let's write this monad instance, starting with functor, which is easier. So most of it is pretty straightforward until you get to the lambda. So the lambda probably must be an fmap, just like the other ones, but the type of the function is not completely clear. So put a typed hole, print the error message in a way that fits a slide, and you get something like that. So you have a function f that has type a to b. You can see that as a renaming. We're doing fmap, and we actually need a function maybe a to maybe b. So what would that be? Yeah, sure. Well, it's not very hard, but that's going to, OK. So let's do the monad thing. I skipped over the applicative instance. It's not interesting. So return is evidently var. It's the one way to introduce a variable. And the bind is pretty straightforward until the lambda. So you add in a typed hole again, and you say, OK, I've got a substitution from A to term B, and I want one from maybe A to term maybe B. Any idea? Traverse, absolutely. So that's it. The monad instance is there. The entire point of that is you have basically no choice. You have no reasonable way to fill in these holes besides that one. I mean, if you really want to write something else, of course you can. Error exists, for instance. But really, you can't get it wrong if you're trying to get it right, which is much more than, this is much to say compared to actual De Bruyne indices or named things. There's actually one more funny thing to say, which is that there's another interesting structure that comes out of functors, which is algebra. And like interpreters of your terms, and I use it in a very, very broad sense. So that works for something that will actually be an interpreter, but that also works in that case for type checking, and we'll get back to this. So it will happen to be an algebra of the functor. If you are not used to seeing it that way, you would rather seeing a term of type to type. There's absolutely equivalent via an fmap. It is just the same relation as join and bind. So this is the type of an algebra of the functor, and a compositional interpreter, then, is an interpreter with a bit more structure, is an algebra for the monad, which is the same thing as that, except you need to respect the monadic structure in a fairly natural and straightforward way. If you try to work out these laws yourself, you'll get the right one. Well, that's good. But it gets tedious. I mean, I've got all these code, and I just said, you can't get it wrong. So if I can't get it wrong, I'm not doing really anything interesting. So I'd like it to be generated, which I could just do right now, but I won't, because I want to do something first. And I want to talk about unfixing, which is a programming technique that some people enjoy, probably me, I'm not sure. That says, okay, I'm not going to represent my data type as a recursive data type. I'm going to give a sort of signature that represents my data type in the abstract. And that signature will turn out to be a functor, or any functor. And I take the fixed point of that explicitly. And combining these two things, you can derive properties on the fixed point automatically from properties of the functor. So just being a functor, for instance, you will have a number of recursion schemes like catamorphisms. The sort of canonical example is a list. So let's go through this. List f is the functor representation, or list f of a is the functor representation of list a. It has a nil there that you can think of as the recursive call, but it's abstracted away. You derive that it's a functor. You define list as the fixed point of this. This is exactly the same data, the same in-memory representation as the actual list. So I'll just have changed a bit the way Haskell thinks about it, but not the code. And then catamorphisms correspond to folder. Well, the type is not the same, but up to a trivial isomorphism, that works. So catamorphism just means I interpret each of my constructor and I do a straightforward induction. That is just the natural induction thing that you will do if you don't want to do clever things like going too deep or doing several inductions embedded one to another. It's just called catamorphism to be scary. But anyway, there's plenty of benefits to that. We'll come back to it. The point is, this is really something that I'd like to do today. But I can't quite do it. And to understand why, let's talk in more generality of something called non-uniform data types. The simple example of which I know is the type of complete trees. It takes a bit of a while to figure out why this is actually the case, is a type of complete tree. But the point is that when I call a complete tree again, recursively, I don't call it on the same type A here. I call it, or here, I don't know who's watching. I call it on a pair of A and A. So basically, I'm writing sort of it starts with a bunch of constructors that tell me how deep the tree is, and then it's a pair of pairs of pairs of pairs of pairs of pairs of pairs, and that makes a perfectly balanced, complete binary tree. And this is quite different from list, where the A is always the same. And okay, I thought I had an extra slide, so sorry. The idea here is that when I'm taking the fixed point earlier, I was taking the fixed point of list A of something. So the A was always the same. I considered list A as a thing. So what I was producing was list A, not list. And therefore, I could get away with having a fixed point in star. Whereas in complete tree, I really want to just ignore that in my fixed pointing. Is that a word? But instead, I want to just focus on the complete tree part, the functor itself. So there's no escaping that conclusion that we want a fixed point that returns star to star rather than just star. So to do that, it's not terribly difficult. You just say, you'll just take mu again, the same mu as earlier. You change the data, you change the type annotation. Now it has star to star to star to star. Okay. New types have type star, so I need to add the argument at the end. I follow the type, and there's exactly what I wanted. The mu here is a functor, and I call it. I don't need the a inside the mu anymore. Okay. And then the definition of complete tree as an unfixed data type is completely straightforward. It's just exactly what you would have expected, except as you notice that the arguments compared to list have switched order. I mean, this is not extremely surprising, but okay, it gets interesting when you want to do the catamorphism story again. So we need something to take the place of functors. We need a notion of algebra for the functors, or the replacement of functors. What would that all be? So I answered that question with the power of algebra, and specifically of category theory. So you've heard of the category of endofunctors before, because you've all heard the sentence that a monad is a monoid in the category of endofunctors. Yeah, and I'm going to do slightly worse. So category is given by a notion of objects and a notion of arrows between two objects. I don't want to go too much into the details, but you can think of the category of types that we often call Hask as having star as the objects, the kind of objects, and the arrows being functions from a type to a type. And the category of endofunctors arises when you say, okay, I'm not going to consider types as my objects, but functors. So something of type star to star that happens to be constrained by the functor class. And it's a bit smaller at the bottom there. And the arrows are something called natural transformation, which we can just think of a function from FA to GA, where F and G are two functors that works for every A. So we're having a bit of higher ranked typing here. That will come up. So now I just need to replace everything that I would do with functors, etc., by these types, just substitute types. So you write functor1 class. It's a functor one step up in the rank, and then you replace map by map1. So it takes two functors, a natural transformation between the two functors there, and returns the natural transformations between the image functors. But that's not sufficient. So we'd really like HF and HG to be functors. But F and G don't appear in the definition of the class, so what do we do? Well, you're kind of out of luck. There's really no way to say that, except since 2 weeks ago, because 8.6 has been released, and one of the things that has been released with 8.6 are quantified constraints, which is a way to do just that. So this is a one-slide explanation of what quantified constraints are. It's saying, okay, I'm going to take a constraint as a constraint expression as an expression as a constraint. So now I'm going to say, oh, H is such that for every functor, H of F is a functor. And that's actually my entire class. So this is the sort of thing that I couldn't do before, and I'm super excited that 8.6 let me do. Try it out. It's fun. My point is that it's not purely for fun. We're going to get quite a bit out of this. So we can continue, get this one step up catamorphism by saying, oh, what functors? I need a okay, I forgot a constraint, but no, it's okay. So H is a functor 1, F is a functor. F is an algebra of H. That's the first thing. And then we get a natural transformation from UH to F. And the code is mostly the same as for functors, so this is not particularly interesting. It was just to show you that it was super short. So what I've been doing is just replacing star by star to star and functor everywhere. And quantified constraint let me do the functor bit of this. Otherwise, it wouldn't pan out. It wouldn't work. So a question that we can ask is, okay, does type check fit that story? Is type check of this form? Could we generate something that is a compositional interpreter from a catamorphism? Feels like we should. So if we can't, I've probably done something wrong. I haven't. Uh, so you just introduce a new functor that corresponds to the entire right part of the type checking algorithm. By the way, I say that the type checker returns a type. Usually it's a maybe type because it might fail. I can write untyped terms, but it doesn't change anything to that story. It's just to save real estate on the slides. I call that functor assigned because it's like it takes an environment and returns a value. If R and V are the same, by the way, it's the continuation thingy. So it's actually a monad, but it doesn't really matter for us today. And so then, yeah, we can make a type check algebra by saying I'm taking a term where every like sub-instances have been interpreted as interpreters, and I get an interpretation of the entire term. Sorry, and so if you pass that to Carte1, then you get the type check again, up to a new type conversion. Okay. Oh yeah, what about the monad thing? We wanted the terms to be a monad because we wanted to do this this substitution as well sometimes. That's useful. Let's get back to it. So let's try to work that out. So if you look at the implementation of the monad thing, you will see that var is treated very, very differently from the rest. Everything sort of carries the substitution around, and var just applies it trivially, but doesn't mention var anymore, as it should. But my point is that there's structure there. So we'll exploit that by taking a very high version of either that takes two functors of functors, and returns a new functors of functors. And var is a data type that will represent the variables. And so now we can consider the either of these two things, of either var and the description of the rest. So we just split our description apart in 2 bits. And then we go to the monad definition. So the var part is obvious, and then we have to do something about the rest of the term, so the things that should be carrying the structure. So what do we need to carry the structure? So let's have a look. So I don't remember. I have to watch my slide as well. So we've got a u. That's my term. That takes a description of the rest of the term, and recursively a mu thing. So I've unpacked one layer of my recursive data type, and then I have a substitution that takes a's and returns a mu thingy. So basically, I've got mu in this argument position and in the second argument position too, and I need to sort of somewhat merge them together. So how to do this? Turns out algebra. Let me tell you about strong functors. Strong functor is something that just defined like this. So you have a functor thing somewhere inside a pair, and you pull it out of the pair, and the entire pair is within the functor now. So we don't actually define this in Haskell because it's absolutely trivial. That being said, you'll find strong thingies, and especially strong monads, everywhere in the literature. It's really important. In fact, the fact is, we use strength all the time because the do notation exploits the strength. So if we couldn't write any do things if monads were not strong, but we don't have to prove it because they just are. That's actually a deep result involving enriched categories. It's quite fun, and if you want to know more, come to see me at the break. But functors of underfunctors, well, they're not strong by default. So you actually have to prove it. So you remember the monoid in the category of underfunctor thing? There's a trick in there where you replace the comma, the Cartesian product, by composition of functor. It's also a valid product, and strength are relative to some notion of product. So here, we just define functors, or functors of functors, which are strong with respect to that particular product of functors. Easy. But it turns out it's a very, very natural notion. And so it's just exactly the same thing as strength here, except I've replaced the comma by compose. Yeah? And because it's annoying to play with compose, I'm going to do something first. It turns out that there are very, very few functors that are actually strong like this, and not the one that we're interested in. But if we restrict them to applicative, then that's another story. Of course, we can restrict them. They are now functors from applicative to functors. And as such functors, they are strong. So it's not as elegant as if it was always the same category we use, but it's fine. And to eliminate compose, you do basically the same trick as with bind. We compose with a fmap or a fmap1 here, and we get something like this, which is quite equivalent to here, obviously. Right. It turns out it's exactly what we need, because we now have a functor in the A position and a functor in the recursive position, and we just compose them together. Here we can pass join, and we get a functor with nothing on the argument position at the end. The one thing that I don't like about this is that I really need to pass join, and I didn't find a story to pass in bind, which is much more natural. So actually, when you do that, the algorithms have a bit more overhead. They traverse the terms a bit more. That's a bit unpleasant, but all in all, we are done. We can now define a monad instance for mu of either var and h, whenever h is a strong functor in the category of, anyway. So that works. Still annoying to write all these instances. Didn't get better. So let's turn to generics. Because they will derive a lot of things for us. Though I don't know how familiar you are with generics, but basically you say, here is a representation. I type in something that is canonical, and I can programmably type over, or type level program over, and there's an isomorphism between the two, the A and its representation. So it's basically something as a sum of products. And it does one layer. If you hit a recursive call, you'll find your term again. That's not relevant for us because we don't actually recurse. But that doesn't work. Fortunately, someone thought of it before me. That's good. So there's something called generic one. Hey, the one again. For similar reasons. So generic one allows you to have one extra argument. And this, the reason why it matters is that there's one extra constructor that we use. So sums, products, and composition. Because we can compose two functors. So if we have two things of star, 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 we can compose them. And so if we see something like lam of t of maybe, we get, oh, that's a pity. That's not the right symbol. It should be a dot. So that would be t composed with maybe, all applied to A. And as it happens now, we can kind of prove that if t is strong in a certain sense, and because it's not a functor anymore, but sort of, and maybe is traversable or anything like this is traversable, then this is strong. Yeah, I had nothing more on that slide, so let's stay there for a second. So this proves strength, and so we can start deriving functor one and strong one automatically for everything. You might have noticed that we consider here a type with a single argument, whereas we actually have two in our functors of functors. So for that, I use a monomorphization trick, quite akin to lenses. And I owe that to Chongo Kist, who wrote a nice blog post about that, related to generic lenses, which is a very cool library. Anyway, he does all of that. So that leads an immense amount of incoherent instances, but it's fine. It always finds what you want. You don't really have to look about it. You don't program with them. It's just a package in the library. So then you just ask, you just derive any class, and you can derive strong and functor. And my proof is that is an entire definition of simply typed lambda calculus together with the type checker in that particular style. It's pretty short, I think. Is it short? Well, it's fair, yeah. And half of a third of the space is used to write pattern synonyms, which you will find yourself doing a lot when you do that. And I don't know how to automate. Maybe it should be a convention and use some template Haskell to produce them. I don't know, because it tends to be fairly common. Oh, I didn't. Okay, I didn't do the let thing. Okay, well, it's actually let's use the fact that we have used this unfixing thing, and we won't have to go back to the previous slide and sort of edit that. It's messy. No. Instead, we can use the fact that if I have two algebras of a functor, then algebras of two functors, then I can make an algebra of the either of these two functors. This really shouldn't be surprising. It's a type isomorphism. So that takes 2 lines to write. Then I define let. I define the typing rule for let, and I just combine the two, and I've got a type checker for simply type lambda calculus plus let in a couple of lines. Sorry? That's probably what I was calling type check before. Yeah, that's the type checker, which now returns a maybe, by the way. So, the type, yeah, the type is assigned of type maybe type, I think. So there, and that's kind of the real reason why you may want to use this unfixing thing, is that all inductions are open and you can extend them. So if you're familiar with the expression problem, that's one way to approach this. And it's fairly common in a programming language that you have several ASTs that resemble one another, and maybe with more or less constructors. So that's one way to think about this and to reason modularly about this. So I'm getting to the end of what I wanted to say. So I'll conclude on something about quantified constraints again. They can get interesting. This one is the equality for the mu thing for functors of underfunctors. So it says literally that if H is such that for all F that are such that ec of C is such that implies ec of F of C, and then H is ec 2, then of course mu H is also ec. It's obvious. So, and this equality, by the way, for those who know what that means, is up to alpha conversion. So it's perfectly canonical. Despite that, it is derived. So you have to write deriving instance, blah, blah, because you have to give the entire context. You won't figure it out themselves. But when you do that, the standard equality deriving thing will just work, and it will give you the right equality. So I didn't actually have to write it. It's really not very hard anyway, but it's kind of cool. Does this work? It does, yeah. It's tested. Yeah, and that's kind of thing. So when I saw the quantified constant first, I was like, how can this possibly work? Because I mean, it's a perfectly natural extension from a logic point of view when you are allowed arbitrary backtracking, which is not common in Haskell because that would be slow and very unpredictable. So the instance resolution mechanism of Haskell has a lot of constraints on backtracking, namely that doesn't do any. And that's the reason why it's fairly comfortable to program in it, but then it has that poses some constraint on the way you program. That's completely fine. So adding that, I understand, adds some backtracking to the mechanism, but I've never had any trouble with it. So you can write anything you want. It can tell you sometimes I don't want to write this sort of quantified constraints because I don't really know how to handle them. But apart from that, whenever you write something, it works. And you can derive equality for the lambda calculus from earlier with that, which I've done. Yes?
I'm just wondering if you can put holes in your constraints.
Holes?
No.
What? I'm not sure what that would mean.
Well, if I don't want to type out the whole thing of that.
No, it really can't figure it out. So, no, I don't think it can figure it out. Or maybe you could maybe think of having a hole there, because that's the easy bit. That's a reduction that you get, but it doesn't generate any constraint at a higher order. They need to be given. So that's third order. It's pretty cool. It just works out of the box, no travel at all. No, because it's absolutely, it's absolutely straightforward. That's kind of the point, it's straightforward. So that's about it. Here are a few links for these talks, for this talk and for the library that I just released, which has terrible documentation. It's just the code that corresponds to what I talked about today. And the slides on the second line.
Okay, questions? Yeah.
So does this mean that the Haskell type checker is more powerful than Prolog?
More powerful than what?
Prolog.
No, it's incomparable because you don't have backtracking.
You do have backtracking there.
No, well, not full backtracking. So you can't. I mean, you can't do the sort of thing that you can't program Prolog programs inside the instance solver. It won't work. It will complain of overlapping things, and when you've solved that, it will just take a random path that is not the one it necessarily wants.
Hi, so let's say I wanted to implement a compiler. So I have to figure out some way of representing my AST.
Yeah.
And I could either do the really simple thing that I was taught in FP 101, and just having variables represented by text. And then I could write a renamer. And all of those problems you motivated your talk by would go away.
No.
So I could do that.
Yeah.
And for the rest of my compiler, the parser, the type checker, the code generator, I would get to experience the joy of writing simple Haskell 98, which I think no one in this room believes in. Or I could do this.
Yeah.
Which one should I go for?
Depends. Which one do you prefer?
I think my question was loaded.
So if you do the renamer thing, you have to think about that a lot, which is fine for some things and annoying for others. And it's also pretty hard to do any sort of open recursion with names like this. If you use De Bruyne, open recursion is pretty clear-cut. It's been worked out long ago. So you could do that too. And De Bruyne can be done in Haskell 98 if you really like it. But as I said at the beginning, I've done that before and not necessarily liked it. That being said, this is not entirely serious. You can use that, but it doesn't mean that you have to.
I have three questions actually. So
Three.
One is, can we make this as simple as writing Haskell 98? Is there some kind of a way to have it as a language of a type level, being more flexible, maybe like in a Prolog style? I don't know, maybe. And
I'm not sure. I mean, by construction, I try to make it as non-Haskell 98 as possible. It's hard. I mean, the thing is, so something you can. So there's Lambda Prolog if you want to avoid all of these complications. It handles binders for you. That's no fun. Well, I mean, it works, and some people are quite happy with that. So if you want to have something very simple to do programming languages, Lambda Prolog is one way. Another way is higher order abstract syntax, like 12 likes to do. Yeah. Which are all things that have binders in the language level. Another possibility that never has been quite worked out is having a language with nominal thingies, like full nominal reasoning, which is also another way to handle the binders. So it's just saying, okay, now I have data types and they have binders in them. But then it's not completely clear if you can go higher types and do the monad story or things like that. I don't know.
Other question is, can you precise exactly what is derived in this very complex instance which you have?
The previous one is just the instance. So I write what I wrote, and then I say derive this, and it finds the code for it.
Okay.
So let's say I wanted to build a compiler that's really fast.
Ah.
Should I use these binders? So another aspect, it constantly goes on the binders. Like that's thousands of traversals of my AST constantly going on the binders.
Yeah.
Should I use this or should I use the rapier?
It's probably not very efficient. Haven't tried, but the representation of variables is certainly non-compact because it might be a just of something. On the other hand, you probably don't have that much nesting of lambdas, of binders, maybe 7, 10, 15, something like this at maximum. I mean, the terms are bigger than that, but the number of binders that are nested into one another are probably pretty small. And for this sort of things, linear traversals and lists are typically okay. So I'd assume it's slow, but not awfully slow. If you start having experiencing compiler problems, you might look into using a compact De Bruijn representation, which is about as good as it gets.
Is this a question as well, or no?
What's the type of a function that finds the free variables of a term? Or an environment that maps variables to their values? So which both of these things GHC does quite a lot.
Yeah, it's temA to A. To set of A, to set of A. So A is the type of the free variables of your term. So you.
But I might have, if I'm in the context of lots of enclosing lambdas, I might have lots of variables of different levels of nesting. If I'm in the middle of a term
But A is the free variables, type of the free variables, and when you go under a lambda, the type changes. That's all. So you have some lifting happening, like with De Bruijn's. They're nameless. So the free variables are A, so they're typically something that is of a type that you have chosen to be the type of top-level variables. But if you're if you're in the middle of a term, you have a few maybes, and but because they don't have names, it's the usual problem with De Bruijn. So free variables don't quite mean the same thing as was named. They make more intuitive sense in named context than in De Bruijn contexts. But I mean, it's not a problem. It's just that what we would do.
If you want to substitute for many variables at once, then
you always substitute for many variables at once.
So here it's one at a time.
No, you always substitute for all the variables at once. Oh. You can do that one at a time by taking one and passing the identity for the rest. Okay. But apart from that, it's always full substitution. Bind is a substitution, So no, it's all the variables. Yeah.
One final short question. Yeah.
Yeah.
Yeah, and short answer ideally as well.
So is there a category of underfunctors in the category of underfunctors?
You can go higher if you want, yeah?
Yeah.
Yeah, there's no problem. And the underfunctors of the category of underfunctors are also a category, so you can take the underfunctors of that.
Okay. So I guess it's recursive?
Yeah, you can go up as high as you want.
Can you make a fixed point for it?
Yes, but I must confess I have no idea what you will gain out of this.
Okay.
Well, yeah, you can.
All right.
No.
Yeah, that's a good discussion to have during the coffee break. Thank you.